Okay, let's get started today's class. And then don't forget to check your attendance on Blackboard. Okay. So, what did we learn in the previous class? Instruction, right? So, we learned that instructions are the software and hardware interface. Okay. So, actually, when we mention instructions in this course, so it means the instruction set defined by instruction set architecture. So, so this is the conceptual figure that shows the relation between the instructions and then hardware, the processor hardware. So I mentioned that the processor hardware is designed based on the instruction set defined in instruction ISA document, right? So it means that processor, the hardware can only understand the defined instructions. Okay, so you need to remember that a processor can understand only the defined instruction. If the processor is designed based on the a certain instruction set architecture. And then I also mentioned that in this course, so we will learn about the RISC-V. You can also find the RISC-V ISA manual, the document. So I forgot uploading the RISC-V ISA manual. So actually, so I will upload the RISC-V instructions and architecture manual on Blackboard after this class. So, and then also we can understand the behavior of a processor like this. So instruction is given, like so I mentioned that the instruction is the instructions look like and x1, x2, x3, something like that. So if this instruction is given and then the processor generates output, then I also mentioned that output means change of state. And then actually change of states in changes in data in computer systems. But the instruction just define the data changes in architectural states, and then which mean data in register file. So we will learn in chapter 2 about the register file. Also data in main memory. Okay. So it means that the instruction just define the distribution, the changes in data, changes of data in register file and main memory. So I briefly explain about the features of RISC-V instructions. So then also, recently many industries are very interested in RISC-V instructions and architecture because it's open source architecture. Okay, so if you are familiar with the RISC-V ISA, you can get some more chance to get hired by some companies such as Samsung or Chinese. Okay, so then also I explained that the instruction, actually we use the high level languages. So actually we write code using high level programming languages such as C, C++, or Java. And then I also mentioned that these code need to be translated. So firstly, this code is translated into assembly code. Then actually you can understand the assembly instructions, right? Because the assembly instructions are composed of English characters, right? So we can understand if we learn about the assembly instruction, right? But the computer hardware cannot understand our natural languages, so it should be also translated, and then machine code is generated. The machine code includes only zeros and ones, the digital signal. Okay, so we can translate this assembly code using assembler. Okay. So, as I also explained about the stored program computers, and then I mentioned that these data. So instructions are also data. So we cannot distinguish normal data and instructions. So normal data and instructions both include digital signals, right? Zeros and ones. So we cannot distinguish. So actually, in a computer memory, instructions are also stored. Also, normal data are stored in the computer's main memory. Then, in order to access this instruction, then we need to access this main memory using RISC-V. Okay, that's what we learned in the previous class. So actually, as you know, I think you already received notifications from our Blackboard or some emails. So I posted the first lab assignment. So for this lab assignment, in this lab assignment, you are requested to install RISC-V cross compiler. So why is it called cross compiler? So actually, in the previous class, also in here, we can use compiler to generate assembly code. Actually, this compiler can generate the machine code also. Okay, if we use the GCC, it's a GNU C compiler, then this GCC can generate the assembly code also machine code. So this application, like GCC, is called a compiler. But in the lab assignment, I mentioned the where is the I don't know. So we need to install cross compiler. Why? So and then I believe most of you use Windows system or Mac OS system, right? And so and then I also mentioned that the popular ISA today are x86 and ARM architecture. Okay, so usually Windows PC use x86 processors made by Intel or AMD, and then Mac computers use ARM-based CPU recently. So actually, the Apple used the Intel CPUs for their MacBook or desktop computers, but recently they developed their own processors using ARM architecture. So actually, if we compile our high-level language code using our computer, so let us assume that you are using Windows computer system. So then Windows computer systems usually use x86 processors. So if we compile our high-level language code on our computer and x86 architecture, then this compiler will generate the x86 machine code. Obviously, right? So we compile our code using our computer. That our computer is include the x86 processors. Then the compiler will generate the x86 machine code. So we don't want this situation, right? Because we are learning RISC-V ISA. So cross-compiler is that actually the cross-compiler means is compiler like the RISC-V cross-compiler, the GCC, but this RISC-V GCC can run on x86 architecture or ARM architecture. So it means that on your computers. But this RISC-V GCC will generate the RISC-V assembly or machine code. Okay, even though this RISC-V GCC runs on your x86 or ARM architecture, but this GCC will generate the RISC-V machine code or assembly code. So that's why this compiler is called cross-compiler. Okay, it works on different ISA, but it generates the target different instructions. Okay, so it means that for this lab assignment, you need to install RISC-V cross-compiler. So it's a little bit different from the native compiler, like the GCC. So actually, we can easily install native compilers on your computers, but for the cross-compiling environment, so it's a little bit tricky. It's a little bit tricky, right? So actually, you will require some large space for installing this cross-compiler. Also, this cross-compiler needs to be compiled. So I mentioned, so this is also software and then application. And then in order to use this software, and then also you need to build this software that works on your computers. Then you need to compile this cross-compiler from source code. Okay. So if you are not familiar with the Linux operating systems or command line interface, then it may be tricky. So I know the recently students are familiar with the GUI, also the touch screen-based interface. But you are a computer engineering student, so which means that you will work on computer engineering research or computer system research, right? So which means that you need to get familiar with the CLI, the command line interface, or some programming environment. Okay, so I recommend, if you are not familiar with Linux operating system, I recommend you study and you learn how to use Linux operating system also in this course. Okay, so I will not teach so this course is the computer architecture course, so it's not a Linux operating system course. So I will not teach about how to use Linux operating system. Okay, you need to study by yourself. But I made a very detailed document for this lab assignment. Actually, all processes were checked by my TA, teaching assistant. So again, I believe it will work fine. Okay. So for Windows, actually, if you read these documents, you can find that this all processes are explained based on Linux operating system. So I recommend you to install Linux operating system on your computers. But recently we can easily, so it's very easily, we can easily install Linux operating system using virtual platforms. Okay. So if you are using Windows operating system, then you can use WSL, the Windows Subsystem for Linux. It's very convenient. WSL does not, You can also launch the GUI applications, but the WSL does not support the GUI in that environment. The GUI means the graphics user interface. But you can use the command line interface of WSL easily. Also, you can easily install the Linux operating system on WSL. So if you can click this link if you want to use the WSL. Also, you can use the virtual machine, such as VirtualBox. It's a free tool, it's an open source tool. So, and then if you want to use the VirtualBox, then you need to install Ubuntu operating system on your VirtualBox. Okay, so you can find also link for Ubuntu server ISO. Okay, ISO image. Then you can install the Ubuntu operating system on VirtualBox. But also, please note that the enough disk size. Okay, so we can say actually enough to build the cross compiler, we require a larger than 20 gigabyte or 3 gigabyte of disk space. Very large. So please set the disk space as larger than 64 gigabyte. If you install this Ubuntu server on VirtualBox, if you use the WSL, you don't need to worry about the disk space. But the Ubuntu virtual machine will be installed on your C drive, the main drive of the Windows. So please make enough empty disk space before installing Linux operating system. And then, if you are use Mac operating system, then you can use the virtual machine. And on the Mac operating system, you can use VMware Fusion Player, which is also free. The VMware actually it's not a free application, but for students, so you can use the free version of VMware Fusion. It's called the VMware Fusion Player. So I tested these all processes using VMware Fusion. Also, you can use the UTM, so another free virtual machine platform for Mac operating system. And then I believe most of you are using ARM-based system. But if you are using Intel Silicon, that is the older generation MacBook, may include the Intel-based CPU. So actually, if you are using the ARM-based, the Apple Silicon, then you need to download the Unix server for ARM. Okay. But if you are using the Intel Silicon, then you need to download the Ubuntu server for x86. Okay, so you can find some instruction for how to install Ubuntu on VMware or UTM. Okay, so make enough disk space before installing Linux operating system. Okay, if you install the Linux operating system, so it's not called the install. So if you just set up the Linux operating system, then you can install RISC-V GNU compiler toolchain. Okay. So actually, all processes need to be performed inside of Linux operating system, right? Not Windows, not Mac operating system, right? So after this point, okay, so number 0 is a prerequisite. So you need to install Linux operating system. And then after this point, all processes need to be performed inside of installed Linux operating system, right? So do not try on Windows Mac operating system. Okay, so these are processes, and you can follow the instruction in this document. Okay, also, so you need to set the appropriate configuration such as the architecture. So as you can see, you can find that we are building a RISC-V cross compiler, but then this compiler supports the RISC-32I. So we will learn about the 32-bit integer RISC-V instruction set, right? So it means that you need to also install, or you need to also build RISC-V compiler using this configuration. Architecture program I read only to mind. And then the building will take very long time. Okay, just click some copy and you run this build command. You can just use the make command. Then that's it. So if we follow these instructions, and I believe you can easily install the RISC-V cross compiler on your Linux operating system. Okay, but just remember that it will take a long time. Okay, it will take a long time to compile these source codes. So just remember, so you just note that it's larger than 20 gigabytes, and then it means that you need to compile large source code. Okay. Okay, then we will use the RISC-V ISA simulator. So after installing the RISC-V cross compiler, then we can generate the binary file, RISC-V binary file. Then what's the problem? We can generate RISC-V binary file, okay, it's an execution file, but we do not have RISC-V computers, right? So I mentioned that, so do you understand? So computer hardware, can just understand the defined instruction. So instruction defined by ISA, right? So which means that if we want, so if we run the RISC-V binaries, then we require RISC-V processors. Okay, we require, but problem is that we do not have RISC-V computers, right? Who has RISC-V computers? No, obviously no. So even though we can generate the RISC-V binaries, but we cannot execute these binaries without RISC-V computers. So in this case, we need to use the simulator. Okay. So this is the RISC-V ISA simulator. So which means that this simulator can execute RISC-V instructions using software. Okay. This software just emulates the behavior of RISC-V computers. Okay, but this is software, so which means that it's very, very, very slow. Okay, so very slower than the hardware, but this simulator can execute the RISC-V instructions and generate the defined results. Okay, so actually not to run the compiled RISC-V binaries, we need to use the simulator called Spike. It's called Spike. So which means that you need to also build this simulator, okay, using this command. Okay. And then and then this is just the simulator, and then we don't have operating system. So in order to run some computers, we require operating system, but we don't have operating system. So the RISC-V foundation also supports the very simple and simple and small kernel. So the behavior is very similar to the very simple operating system, but it's very simple kernel. Okay, so which means that you need to also compile this kernel. This kernel is called the PK, it's the proxy kernel. Okay, so you need to configure the appropriate host is so you need to set the appropriate configuration for compiling this proxy kernel. Okay, so we have now cross compiler, and we have simulator, the ISA simulator, and we have proxy kernel. It's a simple operating system, very simple operating system. And then we can run RISC-V binaries. So this example shows how to compile, so how to generate RISC-V binary. So this is very popular program. So hello and C, the hello world. And then, this is the C code. And then this is the RISC-V compiler. Okay. So you can find the GCC, but this GCC is the RISC-V cross compiler. So you can find some weird name we call the GCC. The RISC-V or good connected to computer and upload ELF. Also, we use the architecture RB32I, and then also you can find some compilation option like the static, and then optimization level is 0. And then if we use the GCC and then -O, you can define the output file name using the -O option. So it will generate the hello binary file from the hello.c. Okay, so it will generate the binary file hello. And then we can use the spike. Okay, this is this spike ISA simulator. You are using the spike, so you can also find the I recording I. Then this is the proxy kernel. Okay, the kernel, like the operating system. And then spike also execute the hello. So PK is also software. So if PK has also RISC-V instruction, but this is the kernel code, like the operating system. And then, so it means that spike will execute the kernel first, and then it will execute the hello, the compiled RISC-V binary file. So you can find the hello RISC-V word. So it is the desired output, right? So print application. As you can see, this code has the print out hello RISC-V word. And then if you run spike using the spike, then you can find that the desired output is ready. So which means we don't have a RISC-V computer, but we can run RISC-V binaries, okay, using simulators. And I also mentioned that the GCC can also generate the assembly code. So actually, GCC is the compiler. The compiler can generate the assembly code first, and then the compiler generates the machine code. But usually, this intermediate state is skipped. The compiler directly generates the machine code. Okay? But if we use the -S option, minus x option, then the compiler will generate the assembly code. Okay. So from the hello.c, this compiler will generate the hello.s is the assembly code. So if you use the cat command, then you can see the content of file hello.s. Okay. And then actually this hello is the binary file. The binary file. Binary file includes RISC-V instructions and required information. Also, this file includes the global data or state data. So, if you want to analyze the assembly code generated by this compiler, then you can analyze this binary file using object command. So it's the application. So if you execute this 532 unknown ELF and the object command, so it is command, and then you can generate the DOM file. Okay. So and then if you generate the hello.dom file, then you can see the content of this hello.dom. Okay, using the cat command. Then you can find that hello is binary file includes large amount of RISC-V instructions. Why? So actually the code size is very small. So the main this is the main function. So it means that if a zip file is executed, the main function will be executed first, right? And then inside of the main function, you can find only printf, the one line instruction, and then this printf will display text, so characters. But the RISC-V instructions will include so this binary hello, the binary file hello includes the many large amount of instructions. Why? So actually this is printf, it's a function, it's a function, right? And then this function is defined in library. So in order to execute printf function, then we require standard IO library, and then actually this library includes the binary code for executing printf function. And when this binary is generated, the binaries in this standard IO library will be included in the final binary. So that's why, even though the code size is very small, the compiled binary includes the large amount of instructions. Okay, so that's why I cannot show the content of hello.dom. So I just show the very simple code. So okay, so this is a very simple code, right? So A is the array. So there are 5 elements in array A, and then we want to calculate the sum of all elements, right? Then sum. This is the main function, and then this sum. So this is also very simple C code. Okay? So it's a high-level language code. Then we can generate the RISC-V binary using compiler, right? So, and then this is the compiled binary file, and then using the object command or instruction, the object actually this is the binary file also. So with the object command, we can get some RISC-V instruction. So actually object down analyze the binary file, and then this object down generate the decoded RISC-V instruction. Okay. So you can find so I cannot show all instructions from the dump file. This is very long. Okay, but I can show the part of the this dump file. So you can find, oh, this is the text section. So we will learn about the meaning of that text. Actually, that text represents the instruction. Okay, RISC-V instruction. Okay, and then so if we use the this line, you can find the main. So which means that this is the start point of the main function. Okay, so inside of this main function, then this main function includes the RISC-V instruction like this. Okay, so but this is the decoded instruction. So actually, binary file includes this part. So what can you see? This part. This is hexadecimal code. So if we just use the binary format, then it will be very long, right? If we just use the 0 and 1, and then this will be very long. So we usually use hexadecimal format, right? The signature code, hexadecimal format. So then we can use the length of this machine code. Okay. So this column just shows the machine code inside of the main function. And then also you can find the decoded RISC-V instruction. So which means that, oh, this is the machine code. So this is the machine code, and then this machine code represent this RISC-V instruction. Okay, add SP, and minus 48. And then this is the machine code, and this is the RISC-V instruction. Actually, binary file includes this part. So you can find the other instruction like this, blah blah blah. Then what is this? This is code. So actually, we need to learn. Okay, so this is PC, so program counter. And then actually the PC is the address of instruction data. So it means instruction code. So what does that mean? So I mentioned that. So computers use code program. So which means our binary file, which means the instructions are also stored in memory. Okay. And then I also mentioned that in order to access the instruction, then we need to access this instruction using address of memory, right? It's obvious, right? So instruction is in the memory. Then in order to access this memory, then we need to know the address for this instruction. It's the same for the apartment or condo. So in order to access some guy or team, the team is in the room number 101, then we need to access this room using this room number, right? This is the address. Okay. So this instruction is in the memory, and then address is 10074. It's also hexadecimal format. So, and then this represents the address of this the instruction, which means that using this address, processor can read this instruction from memory. Then actually, if this address is targeting instruction, and this address is called program counter, PC, my personal computer. PC means the program counter. So using this program counter, the 10074, using this address, CPU with this instruction FP010113 from memory, and then this instruction is given to the processor, and processor executes this instruction add SP minus 48. So we learn the meaning of this instruction later. Anyway, then processor will generate the result. Okay, we find the result. And then after that, the PC to change it to the next line. Okay, what is the next line? What is the next PC? It's 10078. So it goes to the PC to change it to the 10078. Then using this program counter, then this instruction is read from memory, and this instruction is given to the processor. Processor execute this instruction, and that's it. That's how a processor works with instructions. You understand? So this is the PC, and then this is the instruction code, and then by reading instruction code from memory, then the processor can get instruction, and these instructions are executed. So if we just know, so if we can analyze the NUM file, then we can understand how RISC-V instructions are executed. The manner and the instruction is executed. Okay. So that's why actually this is the new part of the lab. In the previous semester, so this lab is newly included semester. Okay. So, but I believe you can understand how the instructions are really executed. So how the high-level language code is translated, and then how the translated instructions are really executed by a processor. Okay. But this concept, actually, you need to understand this concept, so it's important. And then also, you can run the compiled binary using Spike. Okay. So you can also follow these instructions. But also you can find that PC is here. So using the PC, then the Spike also read like the processor. So I mentioned that a simulator emulate means that it's just 모방하다 emulate. So actually this spike just emulates the behavior of a processor. So which means that we can also set the program counter. Okay, enough to execute an instruction, the target instruction, then we need to set the target PC. Okay, so as you can see, the main function, the PC of the main function is the 0001074. So this I set the PC of the main function, right? Then you can run the machine code using Spark. And then we can get some information such as the content of the register file that we. Okay. So, so this is the first lab of this course. Then, if you are not, so I recommend you start this lab as early as possible, because if you are not familiar with the command line interface, then it may be difficult. Okay. So, and then if you have difficulties in this lab or doing this lab, and you can post any questions on Piazza. Just post your question on Piazza, right? So you can get answers quickly by TA. Also, you can visit a TA. Okay? If you want to get help from TA, then you can visit a TA office. And then, the TA office is the Ujang 401C, the TA office, and you can get help from TA. Okay? So please start early for this lab assignment. Okay, any questions? No? Good. So actually, by explaining the lab processes, I just explained the important concept of this compilation process. Okay, so this is the compilation process of the high-level language code. And then also in the previous class, I explained about the stored program. Then in order to understand the stored program, then you need to also understand the PC, the address of the instruction. So actually, you can find that this is the same program, same dump file, and then I already explained. So in this dump file, so you can find the PC, so it's the address of instruction. Then you can find the machine code, machine instruction, and then this is the RISC-V assembly instruction. Then processor also spike the simulator, just change PC. So if the current PC is 10074, it's the current piece, then processor can execute this instruction, and then processor change the PC to the 10078. Okay, so it's the next PC, next program counter. Then a processor can execute the next instruction, 0 to A 12623. Okay, it's a hexadecimal form. Okay. So also you can find that the difference between the current and very next instruction is 4. Okay, so because the RISC-V use hypertext, so which means that the size of this data is 4 bytes. 4 bytes is the 32 bit. Okay, that's why the distance, the difference between this PC and the next PC is 4. Okay, so we will learn later about the size of instruction. Okay, so I already explained about the dump file, and then I hope you can understand the PC, okay, the program counter. Okay, and what is stored in memory? So we are learning about the stored program method or approach. Then what is stored? So in the binary file, so it means that what is stored in a binary file is an executable file. The binary file includes the instruction, and then as I also mentioned that this is called text. Okay. Also in the previous slide, you can find that this section that text, which means that this section includes the instruction. Okay, instruction is a text, just text. And then binary file also includes the data. Which data? Global and static data. So if you see the source code of this program, then you can find that the array A is initialized with this data, right? And then you know this data are static data, right? It's a constant, okay? The static data. So because this data is included in the this data is included in the code, the binary file also needs to include this data. Where? This part. So you can find the here. So I do not show every line of the DOM file, but arrow data section. So this is the data section. Data section also includes the data, okay, the state data or global data. You can find the 100. Okay, it's the same to the 100. Okay, so binary file also includes the global and static data. But sometimes we may use the dynamic data. So dynamic data means that the data can be changed. Also, the assigned memory space can be changed during runtime. So this dynamically allocated memory space is also defined, but it's managed by operating system. So actually, the memory space is assigned to a program when a binary file is launched. So which means that when we execute a binary file, then operating system generate the memory space for this binary file. Then actually the dynamic data space is changed during runtime. Okay. Then how big is the memory of a 32-bit computer? So 32-bit computer means that all variables are represented using 32-bit data format. Okay. It's same for the address. The address can be also calculated by instruction. So it means that the address needs to be calculated from data in instructions. Okay, and then 32-bit computer means that. So we also learn later, but 32-bit computer means it's the size of a register. And then we can generate the address from this register. So which means that 32-bit computer also represents with the size of an address. So address size is the 32-bit. Okay. And then I mentioned the RISC-V use byte address. So which means that address number 1 represents the 1 byte size. Okay, 1 is the 1 byte. Address 1 is the equivalent to the size of 1 byte. So if the address size is the 32-bit, then using the 32-bit address, it can represent until 2 to 32, 2 to the power of 32, it's 4 gigabyte. Right? So 2 to 10 is kilo, 2 to 20 is mega, 2 to 30 is giga. And then 2 to 32 is the 2 to 30 곱하기 and multiplied by 2 to 2, so it's 4 gigabyte. Okay. So it's the maximum size of the memory of the 32-bit computer. Okay, the maximum size of memory is 4 gigabyte. Then address can be replaced from 0 to or F, the 1111111. So it means when an application is launched, then this amount of memory is allocated to the launched application, which is 4 gigabyte. You may think that, oh, my computer has only 1 gigabyte of memory, then what will happen? So actually, we learn about the virtual memory in the memory hierarchy part, but actually this space is assigned to an application virtually. That's why this memory is called a virtual memory. But program the binary file thinks that, oh, I can use this amount of memory space. Okay, for the 32-bit computer, usually for the one application, this amount of memory is assigned from 0 to FF2, 0 FF. Okay, then let's see the structure of the memory space. So when the program is launched and this memory is assigned, so actually so this is just the example for RISC-V. Okay, so actually the different architecture may generate the different memory map. Okay, but this is just an example for RISC-V. So firstly, the exception handler is assigned. Okay, the exception if you a wrong code, so like divided by 0, then this divided by 0 needs to be handled. Okay, so this is also kind of exception. Then exception handler location, the PC, the address of the exception handler is assigned this area, this space. So this is the kernel space actually. The kernel code is assigned to the virtual memory, the application. Also, the upper part, this is also the kernel area. So it means that when a program accesses this address with PC, then the kernel instructions are executed. So just to ignore the kernel part currently, is the kernel part. Then the memory space is assigned to the text. So text is as I mentioned, is the instruction. Then above this text area, then you can find the global data area, one static data area. So which means that the data used by our application are stored in this global data space. Okay. Okay. So actually, this is the static area. So which means that when an application is compiled, then instruction and global and static data will occupy this amount of memory space. Okay, and this is the static data. So which means that this is the fixed data. It does not change during runtime. That means static, right? Does not change during runtime, which means static. Okay. Then other part so this space is assigned to the kernel. This space is assigned to the kernel, and this is this space is assigned to the instruction and static data in the static area of the memory space. Then programmer can use this part during one time. So if you see the this here, then you can find that this is stack. So we can the program, so it's a binary file, the stack point is here. So stack is the temporary space for running instructions. So we also learn about stack later. So this is also very important. Also, we may use dynamically allocated data, such as in a C. So we can use the malloc function, right? Malloc. Malloc represents the memory allocation function. So if we use malloc function, then the memory space is dynamically assigned in this dynamic area. Okay, so in this memory map, this part is dynamically used by program, so used for stack and used for dynamically allocated memory space. Okay, so this is the dynamic data area. Okay, what is stack overflow? It's a very famous site. So not if the size is very small, then stack pointer may encounter the dynamically allocated memory space, then it is called the stack overflow. So stack is the dynamically allocated data. Then the program will work incorrectly. Okay, that is the stack overflow. Do you know stack overflow? Yeah, it's a very famous site for programmers. Okay, so that's the memory map example. Okay, this is the very simple code. Okay, so you can find the function here, and then main function is here. Now, I also mentioned that when this binary file is compiled and executed, main function is firstly executed, and then inside of the main function you can find the two variables fg and three variables fgy, and then the constant value number is assigned to f and v, and then the y just called another function, and then this function is the recursive function. Okay, and then this is the example. So as you can see, this is the address, then this is the machine code. So this is the assembly code. So this is very similar to the dump file, right? Address is a PC, and then machine code on, and then it's a decoded instruction. Okay. And then you can find that this is the func. So what does that mean? This is this part. Okay, so name of this function is func, is func, and then this is the first instruction of the func is the add I and SPSK minus 16. So this is the first line of the func function. Okay, and then what is the PC? The PC is 10144. Okay, then this is the equivalent machine code. So you can find that in here, and then also you can find the return. So return. So if you see the C code, then you can find that some instructions of C is very similar to the assembly instruction. Right? So if we use the return, then actually this is with RET instruction, in RISC-V assembly. And then when the function is called, so it means that this line is it jump to this line, and then this code are executed. Also, you can find the main function here. Okay, so here is the main function. Okay, so here is the main function. So the main function is executed. Then you can find the jump instruction here. Name it, then it goes to the func. So which means function is called by this line. It means it's the function, then it jumps to the function. Okay, so this is the example of the compiled assembly RISC-V assembly code and machine code. So also you can find that the address, the PC of the main function is 10180. So it means that when this program is firstly executed, then PC is changed to this address, the address of main function, and then it's executed. Okay. Okay. So also this is the example. So based on this data, the machine code, okay, and then this, this is maybe small. So you can find the corner part here, and then this is the text part, and then also if the PC is here, then the main function is executed. Okay, so actually in the memory, the instructions are stored like this. Okay, so so these are actually the word. The word means the 4 byte space. So each word of the memory, each word includes the machine code, like here. So if you see this machine code, then you can find that the same machine code is here. Okay, right? I believe so. So I hope you can understand how the program code, compiled machine codes are stored in memory, and then how the PC change it, and then PC map the instructions, the target instructions of application in the memory. Then processor can read the instructions from memory, and then this read instruction can be executed. That's why the control is done by program counter PC. Okay. Any question? Okay. Good. And then let's see how the programs are really translated. So this video shows the compilation step from high-level language code to the code. Okay. So firstly, so we write a high-level language code with editor actually. So we can write some high-level language code such as C or Java, and then using compiler like GCC, and then actually it's GCC, and then minus large assumption. So if we use the minus as large assumption, then the GCC will generate the assembly code. So using compiler, then we can generate the assembly code from high-level language code. And then using assembler, then actually it's a GCC, then we can generate the object file. So this object file just includes the required information like the machine code, and then data, and then some other information is included from this code, our high-level language code. So it is called the .o file, right? So if you compile the .c file, and then if the .c file generate the final binary file, the intermediate object file, then you can find the many .o file from the source code. Okay, so from the source code, the compiler generates the object file. Okay, the independent object file. And then usually, if you just execute the GCC, then actually that object file is generated. Okay? Actually, that S file is not generated usually. Then the library. If you use libraries, then the binary object file, that means the instruction, also instruction and any other information, the object file includes the information or data. The library object file needs to be included. So for example, hello.c requires standard IO library, right? So which means that this standard enough to execute our hello world binary file. Then this hello world binary file needs to include library. So standard IO library file. Okay. So this process is called linking. It's a linking. So which means that because our object file requires library, so it's compiled binary, and then this compiled binary needs to be merged. Okay? This process is done by linker, okay? And then the final executable binary file is generated. Okay? Like the hello binary file. Then if we just execute, if we execute the hello file, the binary file, then this file is loaded to the memory, and CPU can execute this loaded instruction. Okay, that's how the high-level language code is translated, and then there is a merged with the other libraries. The binary files are generated, and then it's executed. So actually, the object module, the object file includes these information, like the header, some information, and then the instruction is a text segment. As I mentioned, the static, and then global segment is also included. Also, we a program use many symbols, and so program may include the comments and some text data, and then these data are also included in this object file. So if you use the -G option, so this is the debug option, then debug information can be also included in the object file. So this is actually the binary file from your source code. Okay, and then this, as I mentioned, the object file, your object file needs to be merged with the other libraries. If you high-level language code include the other libraries, and then using linker, then the libraries are also merged into your object file, and then final binary file is generated. And as I mentioned, then when this binary file is executed, memory space is added to this binary, this executable program. But this is the work by operating system. Actually, the operating system assigns the virtual memory to this binary file. Okay. So this slide summarizes how the program is loaded. So it means that if you just execute a binary file, or if you click the binary file on GUI interface, then the operating system just work with your binary file like this. So firstly, the header or some information is analyzed by operating system, and then virtual address space is assigned. So it means that the memory map is assigned to the binary file. So it's and then the text and then data is loaded to the memory or the boot. So operating system just generates the virtual space. Actually, you need to learn about the virtual memory, not understand the word code. And then the argument. Also, main function also receives some arguments, so like the input parameters. So arguments are set, and then also registers are initialized, and then the main is code. So I mentioned that when a C code, the main function is firstly code. So then it jumps to the main function, and the main function is executed. That's how the programs are executed in a CPU's computer system. Okay, and we can use the dynamic linking. Okay, so I will stop here. Okay, and then I hope you can understand how the machine codes are generated, the machine codes are really executed in a CPU. Okay. Thank you for your attention. See you next time.